Welcome back to the deep dive. Today, we're diving into something really fundamental, something that might just, change how you think about reality itself.
Time.
Exactly, time. What if time isn't this steady, constant thing we all assume it is? We're going to explore this idea called time dilation. Our guide for this is going to be excerpts from The Elasticity of Time, Motion and Gravity's Effects.
A great starting point.
Yeah, so our mission really is to unpack how things like moving really fast or just, gravity can actually stretch or squeeze time, make it speed up or slow down. Depends on where you are. Okay, let's unpack this.
It's definitely one of those concepts that challenges our everyday gut feeling about how things work. It really shows that the universe is, well, far more strange and wonderful than we might think just going about our day.
Totally. So time dilation, let's start simple. The basic idea is just that time doesn't tick at the same speed for everyone everywhere.
Right. That's the core of it.
Yeah.
Our intuition screams no way, but physics says otherwise.
And the first big factor here is motion, speed. According to Einstein's special relativity, if you move really, really fast, like close to the speed of light,
Which is incredibly fast.
incredibly fast, yeah, time actually slows down for you compared to someone who's just, standing still. The source uses that classic example, the twin paradox. You've got two twins. One stays put on Earth.
Okay.
The other hops in a super fast spaceship, zooms off, travels around, comes back.
Right.
When they return, the twin who went traveling is actually younger than the one who stayed home. It sounds like science fiction, right?
It really does, but it's real.
But it's real. Scientists have tested this with extremely accurate atomic clocks. Moving clocks do tick slower.
And what's fascinating here is that it's all about perspective, your frame of reference. So
Okay.
from Earth's perspective, yeah, the astronaut's clock is ticking slower. They're aging slower.
Okay.
But for the astronaut on the spaceship, everything feels completely normal. Their watch ticks normally. They feel normal. Time passes just as it always does for them.
So inside the spaceship, it's business as usual.
Exactly. Both perspectives are correct within their own frame. That's the mind-bending part of relativity.
Right. That frame of reference idea is crucial. Your experience of time depends on your motion. Okay, so speed warps time. That's already a lot to get your head around.
It is.
But then there's gravity. Here's where it gets really interesting, I think. How does gravity fit into this picture?
Well, Einstein wasn't done after special relativity. His theory of general relativity brings gravity in. And it says basically that gravity also affects the flow of time.
How so?
The stronger the gravity, the slower time passes.
So more gravity equals slower time.
Precisely.
The source gives this example. Time passes slightly slower at sea level than it does on top of a mountain.
Yeah, that's a good one.
Because gravity is a tiny bit stronger closer to the Earth's center, right?
Exactly. The difference is minuscule, like billionths of a second. You'd never notice it.
No way.
But it's there. It's measurable with those same super accurate atomic clocks.
Wow.
And if we connect this to the bigger picture, it just shows how interconnected everything is. Space, time, gravity, they aren't separate things. They're woven together in this fabric of space-time, as Einstein called it.
Space-time, right?
And even tiny differences in gravity cause ripples in that fabric, affecting time itself.
Okay, so this isn't just like theoretical physics for blackboards anymore. You mentioned measurements. Does this time dilation stuff actually show up in technology we use?
Oh, absolutely. Every single day.
Really? Like what?
Your GPS. The system you use for directions in your car or on your phone.
My phone's GPS. How?
Well, think about the GPS satellites orbiting Earth.
Okay, they're up there, moving fast.
Right. Two things are happening. One, they're moving very fast, maybe 14,000 kilometers an hour or so. So special relativity says their clock should tick slightly slower than ours on the ground.
Okay, that's the speed effect.
But two, they're also much farther away from Earth's center than we are.
So gravity is weaker up there?
Exactly. And general relativity says weaker gravity means time should tick slightly faster for them compared to us.
So you've got one effect slowing time down and another speeding it up.
Precisely. And they don't cancel out perfectly.
Yeah.
Engineers have to account for both effects using Einstein's equations.
No kidding.
Yeah, they constantly adjust the timing signals from the satellites. If they didn't factor in both relativistic effects, the speed and the gravity, your GPS position would drift off by like several miles every single day. It would be useless.
Wow. So GPS relies directly on these century-old theories about space-time warping.
Absolutely critical. It really makes you think, doesn't it? This raises an important question. just how much of our modern world is built on these fundamental and, frankly, weird principles of physics.
It's kind of amazing. So let's try and wrap this up. The big takeaway from the source material seems to be that time isn't this rigid universal metronome we imagine.
Not at all.
It's flexible. It depends on where you are in a gravitational field and how fast you're moving.
Right. It's relative.
And that idea of relativity is key. You know, someone on Earth sees the astronaut's clock ticking slowly, but the astronaut feels totally normal. And the beauty of it, the source says, is that both viewpoints are correct from their own frame of reference.
That's the core of it. Time is elastic, not absolute. And accepting that really does open up your perspective on the universe. It's definitely far more strange and wonderful than we once thought.
So there we have it, time dilation. It's a real measurable thing. Motion and gravity literally warp time. It's one of those concepts that it just kind of blows your mind a bit, doesn't it?
It really does. And it leaves you wondering, so what does this all mean for our perception of a single universal now? You know?
Good question.
If time is different for you, depending on where you are and how you're moving, does it even make sense to talk about things happening at the same time across the universe? Or even, across the street, if you can measure precisely enough? How does this relativity of time change how we think about events unfolding?
That is definitely something to chew on, a lot to think about there.
Indeed.
Well, thank you for joining us on this deep dive into the very elastic nature of time. We hope you keep exploring the surprising ways our universe works.